Okay, so today we're doing Module 5 for AP Calculus BC, and we're going to be covering two topics that will most likely show up on the AP Calculus BC exam, which are Euler's method and Newton's law of heating and cooling. So let's go ahead and get started with Euler's method. Okay, so what is Euler's method? Euler's method is a numerical method for solving differential equations. It's typically used as a method when you're working with a differential equation that cannot be solved with algebra. So it's important to note that Euler's method doesn't produce an exact solution, but rather an estimate based on the use of a series of tiny tangent lines. So some key words that we associate and we need to know for Euler's method are step/increment, which is the distance moved from the initial value for each iteration of Euler's method. And the other one is numerical solution, which is a solution composed of estimated points on a solution curve rather than the equation of a solution curve. So let's go ahead and get into some examples. So if dy dx is equal to negative x over y, and we know that the point 0, 1 is on the solution curve, approximate the value of y when x equals 0.2. Use two steps of equal width. So basically, whenever we have a Euler's method problem, we're going to set up a table like this, where we have our x, y, our slope, our tangent, and our x plus change x, and our new y. So we're given that our point is 0, 1. So we're going to put that in our x naught, y naught column, 0, 1. And we are also given that dy dx, which is our slope, our m, is equal to negative x over y. So we're going to plug 0 over 1, which divided by 0 is slope, or is anything. So if you have 0 divided by anything, you're going to get 0. So our slope is 0. And then we use the basic equation for a line. Y minus y1 is equal to m times x minus x1, and that's the equation we're going to use for tangent. And we're going to plug that in, and we just get y equals 1 for under the tangent column. And then we're going to move on to x plus the change in x, which is the next column, which is kind of like our new x. So we're going to take our x value, which is 0, and our change of x, which is 0.1 in this case, because we have two steps of equal width, and we're looking for the value when x equals 0.2. So our change in x is going to be 0.1 here. And when we add that to 0, we get 0.1. That's our new x. And for your new y, you are just going to plug in your new x value into the tangent, the equation for the tangent line, and then whatever numbers that you spit out that's going to be your new y. So then we get our new y to be 1. And then we go through the same process for the next column. And you find out that when you plug in your new x, which ends up being 0.2 here, you get 0.99 as your new y, so f of 0.2 is approximately 0.99. Okay, so let's move on to our next problem. The solution of the differential equation dy dx equals negative x squared over y contains the point 2, negative 3. Using Euler's method with delta x equals negative 0.2, or your step is going to be 0.2, to approximate y when x equals 1.8 gives y approximately equals what? Okay, so we're going to set up our table again, like we did in the previous problem. So we have our x column, our y column, our slope, our tangent, and our x plus delta x, our x plus delta x, which is our new x, and our new y. And so we're given that a point is 2, negative 3, so we're going to plug 2, negative 3 in for our x naught, y naught. We're going to calculate the slope. We know that dy dx is equal to negative x squared over y, so we're going to plug in our x and our y into this dy dx equation. And we get our slope to be 4 over 3. And then we're going to use this information to fill in the equation for point slope form for a tangent line, which is y minus y1 equals m times x minus x1, which gives the equation y equals 4/3 times x minus 2 minus 3. And we're given that our delta x, or our step or increment here, is going to be negative 0.2. And we're going to add this to our given x coordinate, which is 2, which yields 1.8. We're going to plug this value back into the tangent equation. So we're going to plug this into the x, plug 1.8 1.8 into 1.8 minus 2 times 4/3, subtract 3, and we get our new y to be negative 3.267, which is our answer. Okay, so the next topic we're going to cover is Newton's law of heating and cooling. So basically, Newton's law of heating and cooling is, so some quantities change at a rate proportional to the difference between the existing amount of that quantity and some fixed constant b. Frequently, these problems are related to Newton's law of heating and cooling. So some examples would be falling objects approaching terminal velocity and pressure inside deflating containers approaching outside pressure. So those are some common examples of Newton's law of heating and cooling. So Newton's law of differential equations is going to take the form dy dt is equal to k times y minus b, where b is going to be the fixed constant while k is the constant of proportionality. Some important things to remember are that if k is greater than 1, the quantity is increasing. However, if k is greater than 0, the quantity is increasing. However, if k is less than 0, the quantity is decreasing. So let's jump into some examples. So number 1. dy dt equals negative 0.1 y plus 2 with initial value 0, negative 5. Solve for y using Newton's law of heating and cooling. So this is a pretty straightforward one, but let's go ahead and jump right in. Okay, so we have our dy dt is equal to negative 0.1 y plus 2 and our initial value of 0, negative 5. So first thing we're going to do is we're going to separate our variables. So you multiply y plus 2 over to the other side, and you multiply dt to the right side, and then you integrate. And when you integrate, you get ln of y plus 2 in the absolute value bars. But however, we need to isolate y. So what we're going to do is the inverse of log is e. So we're going to raise the log function to e raised to the ln, so they'll cancel. And then we're going to raise the right side, e raised to the negative 0.1t plus c. So our e and our ln are going to cancel. So we have our y plus 2 is equal to e raised to the negative 0.1t plus c. And then something we can do using exponent rules is we can bring this e raised to the c in front, and as multiplied as e to the negative 0.12, e to the negative 0.1t. And because e raised to the c is some arbitrary constant, we can just designate this as a. And then we can subtract our 2 over. And now we have y is equal to a times e raised to the negative 0.1t. And we can use our initial condition now, and we can solve for our constant a. So when we plug in 0 for t, and we set y equal to negative 5, and you solve, we get a is equal to negative 3. And so we get our final equation to be y is equal to negative 3e raised to the negative 0.1t minus 2. And that's your final answer. Okay, let's move to example number 2. Suppose a casserole is removed from an oven that is 250 degrees Fahrenheit and is placed in a room that is 72 degrees. After 1 hour, the casserole is 200 degrees Fahrenheit. What is the temperature of the casserole after 90 minutes? Okay, so you're going to use the basic equation for Newton's law, or the Newton's law differential equation of heating and cooling, which is dy dt is equal to k times y minus b. And so we know that the constant temperature in the room is 72 degrees Fahrenheit, so that's going to take the place of our b. And then we're just going to solve for y as we did in the previous problem, from calculus AB. And when you solve for y, you get y equals a times e raised to the kt plus 72. And if you dissect the word problem, the oven, it is 250 degrees. And so we can assume that the temperature of our casserole at time t equals 0 is going to be the same temperature as the oven, which is 250 degrees. So we can solve for our constant a. So when you set t equals to 0 and you set your equation equal to 250, you solve a to be 178. However, we're not done yet. We now have y is equal to 178 e raised to the kt plus 72, but we need to solve for k. So we're going to use the other bit of information that's given to us, which is the temperature of the casserole after 60 minutes. So you plug in 60 for t and you set it equal to 200, and when you solve, you get k is equal to negative 0.005495881. And then you can plug this in and you have your full-fledged equation, and you can solve for the temperature of the casserole at T equals 90 degrees.